Hello everyone, welcome to Calc Lesson number 35. Today we're going to be looking at analyzing and graphing polynomial functions. So let's start by recalling the features of a graph that we can determine from the function f of x, the first derivative f prime of x, and the second derivative f double prime of x. So from a polynomial function, we can determine our x-intercepts, our y-intercept, and the end behavior of our graph. Then from our first derivative f prime of x, we can find our critical points to determine where our function will be increasing and decreasing and any relative extrema. And then finally, our second derivative, f double prime of x, helps us to find our points of inflection and the concavity of our original function. So for the next few examples, we're going to analyze the function by filling in any missing information where applicable in the table that will be provided, and you have that handout from your teacher. We're going to make sure that we show all of our work, and then we will just draw a sketch of the graph. Okay, let's go ahead and get started with our first function, f of x equals x cubed minus 3x squared. So we're going to go ahead and fill in this whole table with everything we know about this function, and then we'll sketch a graph of the function. So let's start with f of x and fill in what we know from our function. So because we're looking at a polynomial function, our domain is going to be all real numbers, or in interval notation, from negative infinity to positive infinity. Remember from the previous slide, our original function f of x also helps us to determine the end behavior and our intercepts. So let's identify those before we start taking derivatives. So the end behavior, remember, comes from our leading term. We want to look at our degree as 3 is odd, and our leading coefficient, which is a 1, is positive. So hopefully you remember, if you have an odd positive, odd means your arrows go in opposite directions, positive meaning they're ending up. So our end behavior, using arrows, we can just list as down, up. To find your x-intercept, remember you set your function equal to 0, and to find your y-intercept, you evaluate at 0. Let's start by setting this original function equal to 0. X cubed minus 3x squared equals 0, factoring out an x squared. We get x minus 3 equals 0, so we get x equals 0, multiplicity of 2, and x equals 3. So we get our intercepts at the point 0, 0, and 3, 0, and we don't have to plug in a 0 because that point 0, 0 is going to be our y-intercept as well. And I'm just going to make a note in my chart here that it was 0, multiplicity of 2, and 3, multiplicity of 1, because I know that that changes the behavior on the graph. Now that we've used our original function for everything that we can, let's switch over and take our derivative. So let's take our derivative f prime of x. Because this is a polynomial function, we can do that just using our power rule. Bring our 3 down, we get 3x squared minus 6x. So I'm going to fill that into my chart. Critical points with the polynomial, we just have to take that first derivative and set it equal to 0. So we have 3x squared minus 6x equals 0. Taking out the GCF of 3x, we're left with x minus 2 equals 0. Solving, we get x equals 0 or 2. From here, we want to determine our intervals of increasing, intervals of decreasing, and our relative extrema. We can do those by setting up a number line and plotting our critical numbers on the line, 0 and 2. Remember, we want to test around them, so I'm going to identify my test points. I'm going to use -1, 1, and 3. To determine increasing and decreasing, I care about the sign of the derivative. So let's evaluate f prime of -1. I'm going to plug into that factored form, so it's a little bit easier for me. 3 times -1 gives me -3, and -1 minus 2 gives me -3. Negative times negative gives me a positive value. Also evaluating at 1, we get 3 times 1 is just 3, and 3 minus 2 is just 1, which is, that's not right, 1 minus 2, hold the phone. 3 times 1 is just 3, and 1 minus 2 is -1. There we go, that's a negative. And evaluating at 3, we get 3 times 3 is 9, and 3 minus 2 is 1. That's a positive, so we can identify our function is increasing then decreasing, and then increasing again. So we can list our intervals of increasing from negative infinity until 0, and again from 2 to infinity, and our intervals of decreasing just from 0 to 2. Now we can analyze what's happening to determine any relative extrema. Because we change from increasing to decreasing, we have a relative maximum at where x equals 0. And because we change from decreasing to increasing, we have a relative minimum where x equals 2. Remember, we want to give our relative extrema as a point because that's going to be most helpful to us when we go to plot to sketch our graph. So we want to actually plug both of those x values back into our original function. So let's look at f of 0. Using our original function, that would be 0 cubed minus 3 times 0 squared is just 0. So we have a relative maximum at the point 0, 0. And then also evaluating at 2, we have 2 cubed minus 3 times 2 squared gives us 8 minus 3 times 4 is 8 minus 12 is negative 4. So our relative minimum is at the point 2, negative 4. Okay, so now we've found everything that we can get from our derivative. So let's switch over and take our second derivative. So going from our first derivative, we can again just use the power rule to find f double prime of x. Bringing down our 2, we get 6x minus 6. In order to determine our intervals of concavity, let's set this equal to 0. Oops. 6 times x minus 1, taking out that GCF. So we're going to set up our number line, and we're going to test around that value of 1. So I'm going to test 0 and 2. We're looking at concavity, so we're going to test in our second derivative. F double prime of 0 gives me 6 times 0 minus 6 is a negative value. And f double prime of 2 is 6 times 2 minus 6 is 12 minus 6 is a positive value. So this tells me that I am concave down because my second derivative is negative, from negative infinity to 1. And then I'm concave up because my second derivative is positive, from 1 to infinity. And because we change concavity from concave down to concave up, at that point 1, we have an inflection point, or point of inflection, when x is equal to 1. But again, just like our relative extrema, we want to give that as an actual xy point. So we want to go ahead and plug into our original function, x cubed minus 3x squared. So f of 1 would be 1 cubed minus 3 times 1 squared gives us 1 minus 3, which is just negative 2. So we have our point of inflection at 1, negative 2. So we're going to take all of this information, and on the next slide, we'll go ahead and sketch a graph of this function. Okay, so we're going to use all of the information that we just found to sketch a graph of this function. So I just have a very simple axis drawn for us to use when we draw the sketch. So the way we want to start this is I want to start by plotting any points that I know for sure are on my graph. So looking at what we listed out relative extrema. Those are going to be points on my graph. The point of inflection is going to be a point on my graph, and my x and y intercepts are going to be points on my graph. So I'm going to start by adding those to my graph. So I have a relative minimum at the point 0, 0, and a maximum at 0, 0, sorry, and I have a minimum at 2, negative 4. I also have a point of inflection at 1, negative 2. I have an intercept at 0, 0, which I already have drawn, and then I have an intercept at 3, 0. Okay, From here, I want to go ahead and identify my increasing and my decreasing intervals, so I know that I'm increasing from negative infinity to 0. So in this whole left side of my graph here, I'm going to be increasing. So notice that this matches with my end behavior, which is going to start down. So I know that this definitely has a positive slope. And then it increases again between 2 and infinity. So looking at x equals 2, I know that I'm going to increase. I have to pass through this point and continue increasing, which matches my second end behavior arrow. And then I'm decreasing between 0 and 2. Just a light sketch for now because I don't know anything about concavity. So now that I've identified where I'm increasing and decreasing and the points that I have, I want to go ahead and identify my concave down intervals are from negative infinity up until negative 1. Up until positive 1, sorry. So that's going to be here. So everywhere up until this point, my graph has to dump out that water. So I'm going to curve it downward until that point of inflection. And then after that, starting at 1, I'm going to curve it back upward, so we're concave up, and try to match the rest of my graph. So the graph we're going to end up with curves down, curves around, whoops, cuts smooth through all of these points, and ends up. And we can double check all of the features that we determined. Do they match the graph that we drew? Okay, we're going to do the same thing for this next example. So number 2, f of x equals x to the 4th minus 12x cubed. We're still looking at a polynomial function, which means our domain is still going to be from negative infinity to positive infinity. The end behavior, again, we look at our leading term. Our degree is even, and our leading coefficient, still that 1, is positive. So here we are even positive. Even means our arrows are going to go in the same direction. Positive means ending up. So our arrows should be up, up. Again, remember to find our x-intercepts. We set our original function, we set our original function f of x equal to 0, and to find our y-intercept, we plug in 0. So let's start by setting this x to the 4th minus 12x cubed equal to 0. Taking out an x cubed, we're left with x minus 12 equals 0. So we get x equals 0 multiplicity of 3 and x equals 12. So we have the point 0, 0, which is going to end up being our y-intercept as well, and the point 12, 0. That's everything we get from our original function f of x. So let's go ahead and switch over to look at our first derivative. So taking our first derivative f prime of x, using our power rule, we get 4x cubed minus 3 times 12 is 36x squared. To find our critical points, we can go ahead and set this equal to 0. Taking out our GCF of 4x squared, we're left with x minus 9 equals 0. So we get critical points at x equals 0 and x equals 9. From here, remember we want to test for increasing and decreasing and then analyze for our relative extrema. Whoops. Don't know how that happened. So let's set up a number line with 0 and 9, our two critical numbers. Now remember, we want to test around them. We can test really anywhere we want, like -1, 1, and maybe 10 would be easy values to plug in. Because what we care about is increasing or decreasing right now, we want to look at the sign of our derivatives. We want to look at f prime of -1. Plugging into our factored form, we get 4 times -1 squared is +1, times -1 minus 9 is -10. Positive, positive, and negative give us a negative. F prime of 1 gives us 4 times 1 squared is 1, times 1 minus 9 is -8. Positive, positive, and negative give us a negative. And finally, f prime of 10 gives us 4 times 100 times 1, which is a positive. So when we look at this, we have decreasing from negative infinity to 0, and then decreasing again from 0 to infinity, and then increasing from decreasing from negative infinity to 0, still decreasing from 0 to 9, and then increasing from 9 to infinity. So we can go ahead and fill that into our table that we are decreasing. We're increasing first from 9 to infinity, and then we are decreasing from negative infinity to 0 and 0. I guess we could just combine these all in one, all the way until 9. Now when we go to analyze our relative extrema, because we don't change at 0, we don't have a relative extrema. Because we change from decreasing to increasing, we're going to have a relative minimum at x equals 9. And to find that value, we have to plug it into our original function, f of x. So f of 9 would be 9 to the 4th minus 12 times 9 cubed. 9 to the 4th is 6,561 minus 12 times 9 cubed. Gives us a negative 2,187. So we have a relative minimum at 9, negative 2,187. And because we never switch from increasing to decreasing, we have no relative maximum. So now we've analyzed everything we can with our original function f of x and with our function, or our derivative f prime of x. So now we want to switch over and look at our second derivative, f double prime of x. Remember, we take our derivative of our first derivative using our power rule. Bringing our 3 down, we get 12x squared minus 36 times 2 is 72x. From here, we want to locate our intervals of concavity. So let's start by setting this equal to 0, 12x squared minus 72x equals 0. Taking out that 12x, we're left with x minus 6 equals 0. And we find those zeros to be at 0 and 6. We can go ahead and set up our number line. Remember, we want to test around these values. I'm going to stick to negative 1, 1, and 10. Because we're looking at concavity, we're testing in our second derivative. Let's look at f double prime of negative 1 would give us 12 times negative 1 times negative 1 minus 6 is negative 7. Positive, negative, negative gives me a positive, so that's going to be concave up. F double prime of 1 is 12 times 1 minus 6 is negative 5. It's going to be negative. That's concave down. And then finally, f double prime of 10 gives me 12 times 10 minus 6 is 4. Positive, positive, positive stays positive, which means we're concave up. So we can write our intervals of concave down is only between 0 and 6. And then we're concave up from negative infinity to 0 and from 6 to infinity. Because we change from down to up and then up to down, both 0 and 6 are going to be points of inflection. But remember, we want to actually find those points on our original function. So let's look at f of 0 would be 0 to the 4th minus 12 times 0 cubed is just 0. So we have a point of inflection at 0, 0. And f of 6 is 6 to the 4th minus 12 times 6 cubed. 6 to the 4th minus 12 times 6 cubed. Sorry, 6 to the 4th minus 12 times 6 cubed is negative 1,296. So we have an inflection point at 6, negative 1,296. So we found all of this information, and then on the next slide, we're going to go ahead and sketch a graph of this function. Okay, so just like for number 1, I started a new slide. I brought over all of the information that we just found, and I set up an axis so that we can go ahead and sketch this graph. Now, I set mine up using a scale. I just counted to 15 on my x-axis, and then I counted by 500 on my y-axis because I was looking at some of the values I was going to have to graph and realized I wanted to make sure it would all fit. So go ahead if you need to pause the video and sketch out an axis for yourself. Once you've done that, we're going to start just like we did in the last one, and we're going to identify points that are actually on our function. So we don't have a relative maximum this time, but we do have a minimum at the point 9, negative 2,187. So I'm obviously going to have to estimate a little bit, going over to 9 and down to a little bit below 2,000, adding my point. I also want to identify my points of inflection at 0, 0. And then at 6, negative 1,296, another little estimation for me, over to 6, and then down to about that midway point between 1,000 and 1,500. And then finally, looking at my intercepts, I have 0, 0, and just take note that that's a multiplicity of 3, so see what you remember from Algebra 2 and Pre-Calc about that. And then the point 12, 0, so I can go ahead and add that to my graph as well. So we're starting out with these 4 points. From here, I want to look at increasing and decreasing and make sure it matches up with my end behavior. So I'm supposed to be increasing only between 9 and infinity. So starting over when x equals 9, I should have a positive slope, and just make sure I cut through the right point there. And then decreasing everywhere else. It's pretty bad. Let's try that again. All right, well, we'll figure this out. It does match my end behavior up, up, so I feel good about that. Finally, now I want to look at my concavity. Now I'm supposed to be concave down everywhere, or only between 0 and 6. So between my axis here and 6, this is the only place where I'm supposed to be dumping water. Everywhere else I'm supposed to have that concave up. So I want to think about this as being concave up for the rest of my graph. And then I want this part here in the middle to be concave down. So kind of a rough sketch in the purple there. But hopefully what you remember about multiplicity 3 is that you have that curve, that changing concavity as it crosses the axis. So we can draw this graph just a little bit smoother, crossing smoothly through, changing to be concave down, changing back to be concave up, and all the way through. So take a second, look through this graph, make sure that yours looks similar and has all of these same features. Okay, great job with this lesson. Homework 35 is actually a worksheet that your teacher should have posted for you where you're going to practice analyzing and graphing polynomial functions.